Hi, today is December 30th, 2024, and this is the first video of a new series, Introduction to R Programming. To keep each video relatively short, I will only cover a couple of topics in each video. Today, we will only talk about R variables and operators in R. So R has symbolic variables, which are names that can be used to represent values. For example, we can assign the value 6 to a variable x. We can use this expression. So in particular, this operator is the assignment operator, less than and hyphen. So it's like an arrow. We assign the value 6 to the variable x, and immediately we can type x and R will return the value of x. Alternatively, we can just use the equal sign. For example, y equals 3, then y is 3. We can also define new variables using existing variables. For example, we can define a new variable z, which is the sum of x and y. And then immediately we type z, we get a value of z, which is equal to 6 plus 3, which is 9. By the way, if we want to put two statements in one line, we need to use semicolon to separate them. There are some limitations about variable names. So a variable name must start with a letter and can be a combination of letters, digits, period, and underscore. One exception, it can actually start with period, but if it starts with a period, it cannot be followed by a digit. For example, .3b is not a valid variable name. Try to avoid naming a variable starting with period. And then a variable name cannot start with an underscore. And variable names are case sensitive. So in general, R is case sensitive. So for example, age, lowercase h, and capitalized H, these are three different names. And there are some reserved words in R that we should avoid when we name variables. For example, logical values, true, false. And null, this is a reserved name to denote an empty list. And if else, these are keywords in a conditional statement, and some other things that we should try to avoid. For example, C is a function we can use to create vectors. Now let's talk about operators in R. So there are basically four types of operators: arithmetic, logical, relational, and some other operators. First, arithmetic operators, basic ones, plus, minus, multiplication, division, and power. And there are some special operators, for example, modulo, which will calculate the remainder. For example, if we calculate 1 plus 2 times 3 minus 6 divided by 2, we get 4. And then 10 modulo 3 is 1, because when 10 is divided by 3, the remainder is 1. So R can be used as a calculator. Second group, relational operators or comparison operators. They are quite familiar for us: less than or equal to, greater than or equal to, and equal to. So pay attention to this. So we need to use double equal to denote equal to for relational operators, and not equal to is denoted in this way. Let's see some examples. We can compare single values. A is equal to -5, B is equal to 2. Then if you want to check if A is less than B or not, just type it. We get true because A is indeed less than 2. How about comparing two vectors? So suppose V1 is a vector of three different types of values: true, 0.1, and apple. This is a character value. And then V2 is 0, 0.1, and bat. By the way, C is used to create a vector. C means concatenate. We will talk about it in the next video. And then if we want to compare V1 and V2, R will do the comparison element-wise. Basically, it will compare the first element of V1 with the first element of V2. Okay. So how to compare true with a number? So in R, true is equivalent to the number 1, and false is equivalent to 0. So that's why we got false. The first logical value we get is false. And then 0.1 and 0.1, they are equal. So 0.1 is not less than 0.1. So we get false for the second value. Then how about character strings? Apple and bat. Character strings are ordered alphabetically. A is lower than B alphabetically. That's why apple is less than bat. So we get true in the third value. So when we compare two vectors, the comparison is done element-wise. Next group, logical operators. The first group is element-wise logical operators, and, or not. So you can either use the letter and, or you can use the operator and, or a vertical bar. Okay, not, we use this exclamation mark. Okay. So for example, let's define two vectors. V1 is true and true. V2 is true and false. Then let's check V1 and V2. Logical AND. R will combine the logical values element-wise again. So first combine the first element of V1, true, and the first element of V2, which is true. So true and true, of course, is true. And then combine true and false, the second elements of the two vectors. So true and false will yield a false. Because for logical AND, only the combination of two true will yield a true. So that's why it's called element-wise logical AND. It will combine the two vectors of logical values element-wise. So similarly, element-wise logical OR works element-wise. For example, V1 or V2. So true or true, true. True or false, true. And lastly, not V1. So V1 is true and true. So not V1 returns false and false. Next subgroup, logical operators, double AND and double OR. So let's first try to combine two vectors of logical values together using logical AND, double AND. Turns out that we get an error. And so you see length equals 2 in coercion to logical 1. So this one won't work. So now let's combine two logical statements together. 3 is less than 5, true. -1 is greater than -5, true. So true and true yields a true. So this double AND can only combine two single logical values. It cannot combine two vectors of logical values. Similarly, logical OR, double bar, it can only combine two single logical values. 3 is greater than 5, false. -1 is greater than -5, true. False or true will yield a true. Some other operators. First, membership operator, in, percent in percent. This operator checks if element of one object is in another object. Let's see, x is a single value 5, v is a vector, true 5 apple, and if we check x is a member of v or not, we get true, because 5 is indeed a member of v. What if the first object is also a vector? Let's see. Y is a vector, false, and 5, and V stays the same. Then if we check Y is in V or not, it will check each element and see if it is in V or not. So the first element of Y is false. False apparently is not in V, so we get false. And then 5 is in V, so we get true. So this membership operator works element-wise. It will check each element in the first object and see if it is a member of the second object. And another special operator is matrix product operator. Percent, multiplication, percent. So let's see. We define a matrix, a 2 by 3 matrix called M, and then we transpose it, call it MT. So MT is a 3 by 2 matrix. Then if we multiply M and MT together, we should use this operator. In the third video, we'll talk about how to create matrices and other data structures in R. But for now, we can just use the function. And this operator not only works for a matrix and the transpose matrix of it, it can be used to multiply any two matrices as long as their dimensions match. So for example, we can define an identity matrix I, a 3 by 3 identity matrix, and then we can multiply M by I because M is 2 by 3 and I is 3 by 3, so we can multiply them together. Alright, that's all for this video. In the next video, we will talk about data types and vectors in R. Thanks for watching. See you next time. Hi, today is December 31st, 2024. We will continue to talk about R programming. Today, we will talk about R data types and vectors. There are 5 basic data types in R: numeric, integer, complex, logical, and character. So first, numeric. This is basically real numbers. For example, 10, 10.1, negative 88. So the numbers can be positive or negative, with or without digits. And the second type is integer. This is kind of special. We rarely see in practice. For example, the integer 10 is denoted by 10 capital L. This L declares that this is an integer. Okay, so you must add L at the end of the number to indicate that it is an integer. Otherwise, it will be assumed to be a numeric value. Complex. For example, 2 plus 7i. In this case, 2 is the real part, 7 is the imaginary part, and I is used to denote square root of negative 1. And logical, true or false. You can also use the abbreviation of them, T and F. Lastly, character. Obviously, you have to use quotes to wrap character values, either double quotes or single quotes. And it doesn't matter how long the value is. As long as you wrap them in a pair of quotes, it is assumed to be a character value. For example, we can assign the integer 10 to a variable x using this expression, 10 capital L. If we print x, we see this 10. It's similar to a numeric value. If we check the class of it, we see it's an integer. What if we just assign 10 to a variable? For example, y is equal to 10 without this L at the end. Then when we print y, we see 10. It's the same with what we got earlier. However, if we check the class of y, we get numeric. So see the difference between an integer and a general numeric value. Objects. So in R, an object is anything that can be assigned to a variable. It can be of different data types, and it can be of different shapes. There are 4 types of objects: single values, vector, matrix, and arrays. Basically, all of these are arrays. A vector is a one-dimensional array. A matrix is a two-dimensional array. And there are higher dimensional arrays, 3 or more, but we rarely use them. List is a special object, and then data frame. So in today's video, we will focus on vectors. There are three types of vectors based on the data type it contains: numeric vectors, character vectors, and logical vectors. Numeric vectors are also called data vectors. For example, we can assign a vector of numbers to a variable called weight. So apparently this weight vector contains the weights of 6 people. Notice that we use the function C. C stands for concatenate, joining items end to end. And R handles the entire data vector as a single object. For example, if we create a new vector, height, with also 6 values in it, and immediately we can calculate the BMI of these 6 people using this formula, weight divided by the square of height. We can just treat vectors as if they are just single objects. R will do the calculation element-wise. So for example, 60 divided by 1.75 square is equal to 19.59184, etc. Then logical vectors. So logical vectors contain logical values, true or false. We can also use the abbreviation of them T and F. For example, we can create a logical vector L, which contains 4 logical values, T, F, T, T. And if we print it out, we see the 4 values. Sometimes a logical vector is a result from relational expressions or comparison expressions. For example, we got a BMI vector from the previous slide, right? 6 numbers. And if we compare BMI with 25, then we get a vector of logical values. Basically, this comparison is also element-wise. It will take each element in BMI and compare it with 25. So the length of the result depends on the length of the vector in the comparison expression. Character vectors. A character vector contains text strings, and each element is specified in quotes. For example, we create a short vector of student names, Abby, Becky, and Kathy, and then type it. And there are 2 built-in character vectors in R, lowercase letters and uppercase letters. If we type letters in R console, you will see the 26 lowercase letters will be printed out for you. Similarly, if we type capital letters, we see the 26 capital letters will be printed out for us. And there is a special type of vectors, factor type vectors. Sometimes categorical variables are coded as numeric variables. For example, we create a numeric variable called pain, which contains 5 values. These numbers 0, 1, 2, 3 are used to represent pain levels. And if we apply the summary function on the vector, the 5-number summary and the mean will be calculated for us. Because the vector is numeric when it was created. However, we know that these numbers represent levels instead of numbers themselves. Namely, the difference between 1 and 2 and the difference between 2 and 3 may not be the same. So the difference among levels may not be the same. In this case, it's better to convert this numeric vector into a factor type vector so that the variable can be treated as a categorical variable. In R, we can use a factor function to encode the vector as a factor. The syntax is very simple. We can just put the numeric vector in the function and then specify the levels. In this case, only 4 levels, 0, 1, 2, 3. Then we name it F pain, factor type pain, and then type it. So you see the first row is the same with the original pain vector, but there is a second row which shows you the levels of this factor vector. If we apply the summary function on this factor type vector, you see the frequency of each level is calculated. Instead of calculating the 5-number summary and mean, the frequencies are calculated. So this is a distribution table for this categorical variable, which makes more sense. Notice that although we have encoded the vector to a factor type vector, the levels are represented by integers still. To make them more interpretable, we can redefine the levels using character vectors. For example, we can just use the levels function. So this one can be used to redefine the levels of a factor type vector and then specify the character levels correspondingly. So none is corresponding to the previous level 0, and mild 1, medium 2, severe 3. And after this process, redefining the levels, when we type fping, we'll see it looks like this. So all of the levels are represented by character strings now. Alternatively, we can label the levels using character strings when we convert the vector. So you see we get the same result. Next topic, missing values. In R, missing values are denoted by NA without quote. And NA is a valid value in R. For example, we can define a vector x with a missing value in it. Functions in R have special actions when they encounter missing values NA. Most likely, whenever they encounter a missing value, they will yield a missing value. For example, if we apply the min function on x, then we get a missing value. So missing values are contagious. Whenever there is one missing value in a vector, then the result will be a missing value. To avoid this situation and get a valid result, we can specify this argument, na.rm equals true. So this argument will let the min function ignore missing values and calculate the mean only use valid values in x. So you see we get a valid result too. The mean of 3 and 1 is 2. There are some other functions dealing with missing values in R, na.omit, na.exclude, etc. You can just type $na.omit in R console to see more information about these functions. So there are some functions in R that provide information about vectors. The first group shows basic properties of vectors. For example, the length function will show the number of elements in a vector or a list. So by the way, a list is also one-dimensional. And the class function returns the class of an object. The class of an object determines what functions can be applied to an object. The mode function returns the mode of an object. The mode is corresponding to the basic data type of an object. For example, numeric, complex, integer, or character, or logical. And there are also some functions that we can use to check the basic data type of an object. Is.logical, is.numeric, etc. And then we have a function called is.null. This one determines whether an object is empty. Okay. So in R, null is used to represent the list with zero length and is often returned by expressions and functions whose value is undefined. And is.na function determines if an element is missing, na or not. So let's see some examples. X is a vector with 3 elements. The last one is a missing value. If we apply the is.null function on it, we will get a false value. That's because X is not empty. Though the last value is missing, X still has 3 elements. So we get a false value. But if we apply the is.na function on X, we will get 3 values, false, false, and true. That's because the first 2 values are valid values. They are not missing. And the last one is missing. So false, false, and true. So apparently, the length of the result of this is.na function depends on the length of the object we feed into it. And the second group of functions that provide information about vectors are aggregation functions. So they are math or statistics functions. For example, sum, mean, range, minimum, maximum, summary, table, etc. Okay. So table is used to summarize categorical variables. The sum, mean, minimum, maximum functions will only return a single value. And the range function will return two values, the minimum and the maximum. And the summary function will return the 5-number summary and the mean of a vector. For example, we define a vector x. X is a vector of values which contains consecutive numbers 1 to 100. And if we apply the summary function on it, we get a table like this. Okay, minimum, first quartile, median, third quartile, and maximum. And also the mean of the values. So aggregation functions are used to summarize a vector. The last group of functions can be used to change data types of an object. So as the numeric, as the integer, as the character, as the logical, etc. Then let's see some functions that we can use to create vectors in R. The first function is the C function. We have seen this quite a few times so far. C stands for concatenate. We can use it to join items together end by end. For example, we can create a numeric vector called num_v, and it contains 1, 2, and 3. We can also concatenate letters together, A, B, and C. And C can also be used to concatenate vectors and single values. For example, x is 1, 3, 5, and y is 2, 4, and 6. We can use the C function to concatenate x, y, and 10 together, a single value 10 together. And the second function is the seq function. So this one is used to create equidistant series of numbers. The basic syntax is seq from equals, to equals, by equals 1. So the from and to arguments don't have default values. You have to specify them. And the last argument, by, has a default value, which is 1. This is the jump in the sequence. For example, if we want to create a sequence of consecutive numbers from 0 to 10, we can use seq 0, 10. If we want the jump to be 2, then we add an argument at the end. We add a by argument at the end, 2. Then we have a sequence of consecutive even numbers between 0 and 10. And we can also choose to add argument names in the function. If we do so, we can change the orders of the argument. We can say seq by equals 2, 2 equals 10, from equals 0. We can change the ordering of the arguments. If the step size is 1, we can use the shortcut syntax 0, 10. This is equivalent to seq 0, 10. And the series can also be in descending order. For example, 100, 90. We have this sequence of numbers from 100 to 90. The third function that we can use to create vectors is the rep function, the replicate function. This one can be used to generate repeated values. For example, if we want to generate a vector of ones, 10 of them, then we can say rep1, 10. Okay. And the first argument is the value or values we want to repeat. And the second argument specifies the time or times we want to repeat the value. And we can also repeat a vector of values. For example, V is a vector of A, B, and C. If we want to repeat V 3 times, we can use this code. Okay. Then you see the entire vector of V is repeated 3 times, A, B, C, A, B, C, and A, B, C. We can also repeat elements in a vector different numbers of times. For example, if we would let the second argument times to be 1, 3, so basically 1, 2, and 3, then we will repeat A once, and repeat the second argument B twice, and lastly repeat the third argument C 3 times, and we got this. So it's a very flexible function. And lastly, the replicate function is often used for grouping. For example, if it is known that the first 5 observations in the dataset are men and the last 10 are women, we can use the REP function to form a vector where 1 represents men and 2 represents women. So we can do this REP 1, 2 and C 5, 10. So this means we will repeat 1 5 times and 2 10 times. Lastly, data types in a vector. Theoretically, the elements of a vector must have the same data type. If you concatenate elements of different data type together, all the values will be converted to the least restrictive data type. For example, if we concatenate the logical value false and a numeric value 2 together, then if we print it out, you will see the false value is converted to 0 automatically. As I said before, in R, false is equivalent to 0 and true is equivalent to 1. So that's why false is converted to 0. Similarly, if we concatenate a numeric value 2 and the character value A together, then 2 is converted to a character value. So you see a pair of quotes is added to 2. From this example, it's very obvious that logical values are the most restrictive, while character values are the least restrictive. Alright, that's all for this video. Next time, we will talk about other data structures, matrices, data frames, and lists. Thanks for watching. See you next time. Hi, today is December 31st, 2024. We will continue to talk about R programming. Today, we'll talk about matrices, lists, and data frames. First, matrices. A matrix is just a two-dimensional array of numbers. In R, the matrix can have other types of data. Matrices and arrays are represented as vectors with dimensions. For example, we can create a matrix as follows. First, we create a vector of numbers, x, which is numbers from 1 to 12. And then we specify the dimension of x. C3, 4. That means 3 rows and 4 columns. Then if we print out x, we'll see a matrix like this. So the dimension function sets the dimension x to be 3 by 4. Consequently, x becomes a 3 by 4 matrix. Originally, x is a vector, one-dimensional. And notice that the storage is column major, which means by default, the elements of the matrix are filled along the columns. You see 1, 2, 3, 4, 5, 6. So this is the default behavior, but we have the option to change it. We'll see in a moment. The second way to create a matrix is to use the matrix function. So let's see, we can create a matrix which is exactly the same with the one we just seen using the matrix function. Okay. So we call it M1, and there are 3 arguments, 1, 12, and 3, and 4, right? By default, the 3 arguments of the matrix function are data, number of rows, and number of columns. Okay. Where data usually is a vector of values. In our example, the data is the 12 consecutive numbers from 1 to 12. And also, in the matrix function, the elements are filled along the columns by default as well. If we want to change this behavior, we want to fill the matrix in a row-wise fashion, we can add one more argument. By row equals true. Then you see the elements are filled along the rows. Sometimes we might want to add row names or column names to a matrix. We can add column names using this function, COL names, column names. Just list a vector of character strings for the column names. For example, suppose we want to name the 4 columns A, B, and C, and D. We can just use the first 4 letters of the letters vector built in R. Similarly, we can add row names using the row names function. As you see, we add 4 row names to the matrix. Matrices can be transposed using the T function. We actually have seen this before in last video. It's very simple, just lowercase t. After we transpose a matrix, the original rows will become columns. You see, 1, 4, 7, 10 is a row in M1, and it becomes the first column in the transposed matrix of M1. Okay. And similarly, the columns will become rows. I see 1, 2, 3 is the first column originally, and now it's the first row. Yet another way to create a matrix is to use the cbind or the rbind function. Cbind stands for column bind. So basically we combine columns together, or we bind columns together. So you see, we first created 3 vectors, A, B, and C, and then we can just apply the cbind function on them and create a matrix M4. Okay, 3 columns. Similarly, we can use the rbind function to stack them together to create a matrix. So in this case, we will bind them as rows. Okay, so A, B, and C. We can also add more columns or more rows to a matrix using the cbind or the rbind function. Just make sure that the dimensions match. For example, M4 is a 4 by 3 matrix, right? Then we can add a column of a vector with 4 elements, okay, using the cbind function. So just put the matrix and the new vector. Just make sure the number of elements in the new vector and the number of rows in M4 are the same. Similarly, we can add rows using the rbind function. Next topic is lists. Definition. A list is a combination of objects. Lists are a very flexible data structure in R because the components of a list may or may not be the same data type, and they may not have the same shapes. For example, we can create a list as follows. We first create a variable with a single value, x, and then a vector of letters, the first 5 letters, A, B, C, D, E, call it LV. And then we create a 3 by 3 matrix, call it M. We can put all of them together, okay, wrap them in a list. Just use the list function and then put all of the components in the parentheses, call it L. Then if we print out, we see this is a list. So see, the components of L have different data types and different data structures. So lists are very flexible, and many R building functions return their results in the format of a list. Now let's see how to slice lists. We can retrieve a list slice with a single square bracket operator. Okay. For example, if we want to extract the second component of the list, we can use L bracket 2. Okay, so then the second member of L is extracted, which is exactly LV, okay, the 5 letters, and the result is a sublist. If we check the class of it, it's a list. It will not return the data types of the data. It will instead tell you that it's a list. And if you check the length of it, it's 1, which means this is a sublist with length 1. If we want to reference a list member directly, we should use the double square brackets operator. For example, if you use L double square brackets 2, we can directly access the 5 elements in LV. If we check the class of the 5 elements, we get character. Okay. And if we check the length of it, 5. We can modify list members using the assignment operator, equal or less than hyphen, the assignment operator. Suppose we want to replace A by W in the second component of L. We can just do the following. So L double bracket 2. So this part has 5 letters. And then we refer to the first element, which is A. And we assign W to the first element. So consequently, we use W to replace A. And the last data structure we'll talk about is data frames. So a data frame is a list of vectors of the same length that are related across. So from this definition, we know that a data frame is a list, and the components are kind of special. They are all vectors of the same length, and the data are related across horizontally. So basically, data frames are always two-dimensional tables. We can use data.frame function to create a data frame from pre-existing variables or vectors. For example, we have two vectors, weight and height. Just make sure that they have the same length. And then we can just apply the data.frame function on them and save the result as df and print it out. You see, it looks like this. So a data frame is a list of vectors of the same length. And the data are related across. So each row is corresponding to one individual. So they are related. And how to access components in a data frame? First, we can use the dollar operator. So suppose we want to extract the weight column. We can just say df $weight. Alternatively, we can use the column index using the square bracket operator. So notice that we use df square bracket comma 2. Because data frames are two-dimensional, we should specify the row index and the column index. But if we want to extract all of the rows, then we leave it open. But still, we need to use a comma to separate the row index and column index. Now, let's talk about subsetting. First, vectors. Vectors are one-dimensional, so we only need one index to subset a vector. For example, if we want to extract the second component of weight, we can just use the square bracket operator, weight 2, and get the second component. We can also choose multiple elements. If the elements are not consecutive, the indexes are not consecutive, then we should use the C function to create a vector of indexes. And then you see the first, the third, and the fifth elements are extracted. And if you want to extract the first three elements, you can use this notation. And 1 column 3 is 1, 2, 3. Next, matrices and data frames. Matrices and data frames are two-dimensional, so we need to specify both the row index and the column index to extract values from a data frame or matrices. So let's see, df is a 6x2 data frame. I suppose we want to extract the height of the first individual. We should use df square bracket 1, 1. So first row, first column, so this number. Similarly, if we want to extract the weight of the third person, we should use df3, 2. We can also choose an entire column or an entire row. If we want to select the first row, for example, we use df square bracket 1, bracket. So again, if we want to extract the entire first row, that means we want all of the columns of the first row. So we can omit the column index, but we still need to use a comma here to indicate that df is a two-dimensional object. So we still need two indexes. Similarly, we can extract the first column. And we can also choose a subset. Okay, so first two rows and first two columns, which are exactly these four numbers. Many times it's very useful to use some condition to select rows or filter rows. For example, suppose we want to choose observations with height greater than 1.75 meters. Then we can use a relational expression in the row index part, in the square bracket. So df height is greater than 1.75. This expression will yield a vector of true or false value. And whenever the row has a true value, that row is selected. Sometimes we might use two or more conditions to choose rows. In this case, we need to use the element-wise logical operators to combine those conditions. For example, we want to choose observations with height that is greater than 1.75 and weight that is less than 80. Then we can combine them using this AND operator. So this element-wise, only this element-wise logical operators can be used to combine vectors of true or false values. And then you see this is the result. The height should be greater than 1.75 and the weight should be smaller than 80. And lastly, there are two functions, built-in R functions, that we can use to choose the first few rows or the last few rows. The head function can be used to choose the first 6 rows by default. And you can also choose other number of rows. For example, you can choose 3 rows instead of 6. And the tail function will show the last 6 rows by default. But you can also choose to show the last 2 rows or 3 rows or 10 rows. Alright, that's all for this video. In the next video, we will talk about conditional flow. If, else, else, if. Thanks for watching. See you next time. Hi, in this video, we will continue to talk about R programming. There are some important components in R coding: condition and control flow, loops, self-defined functions, and the apply family of functions. In this video, we will talk about conditional flow. The basic conditional construction in R is the if-else statements. The syntax is if parenthesis condition action 1 else action 2. Condition is a conditional expression and it must evaluate to a single logical value. So this condition can only yield one single logical value, true or false, or T or F. And if the condition is true, action 1 is executed. Otherwise, action 2 is executed. In the case that the program does nothing if the condition is false, there is no need to include an else statement. In that case, the syntax is simplified in this way: if condition action. Let's see one simple example. X is equal to -5, and if x is greater than or equal to 0, y is equal to x, else y is equal to -x. So apparently y is equal to the absolute value of x. Since x is equal to -5, the condition is false. So action 2 is executed. Y is equal to -x. -5 is 5. So y is equal to 5. Sometimes we may have 2 or more conditions in the condition part. In this case, we should use the double AND or double bar, double OR to combine these 2 conditions. That's because, the condition can only yield one single logical value, and double AND and double bar will also yield a single logical value. And A and B means both A and B. So this will only be true if A and B are both true. And double bar means or, A or B. A or B is true if at least one of A and B is true. Okay, so let's see some examples. X is 5, y is 3. If x is greater than 0 and y is less than 0, z is equal to x plus y, else z is equal to x minus y. So in this conditional flow, we create a new variable z, which is based on the values of x and y. So apparently x is greater than 0 will yield a true, and y is less than 0 will yield a false. True and false will yield a false. So action 2 will be executed. Z is equal to x minus y. 5 minus 3 is equal to 2. Then take a look at the second example. Or. The first condition yields true. The second condition yields false. True or false will yield true. So W should be equal to x plus y, which is equal to 5 plus 3, which is 8. So the point is, if we have 2 conditions in an if-else statement, then we should use double AND or double OR to connect them. Sometimes the actions have multiple lines or compound statements. In this case, we should use curly brackets to wrap them together to indicate that these few lines belong to one action. For example, if x is greater than or equal to 0, then y is equal to x and z is equal to negative x. Else, y is equal to negative x and z is equal to x. So in each case, we define two variables based on the value of x. Apparently, y should be equal to the absolute value of x, and z is the opposite of the absolute value of x, which is negative absolute value of x. Okay. So see, x equal to 5, which is positive. So action 1 is executed. Action 1 contains two parts. Y is equal to x, z is equal to negative x. So y is 5, z is negative 5. Okay. The point here is, if we have compound statements in one action, we should use curly brackets to wrap them together. And notice that I added some indentations. R does not insert indentations automatically. You have to do so by yourself. And I highly recommend you to insert indentation in your code because it will make everything very clear. Sometimes there are more than two possible choices. Notice that if there is only one if and else statement, then there are only two cases, two actions are possible. If there are more choices, then we need multiple if-else statements. For example, if we want to convert score grades into letter grades, then we should use this if-else flow. So we will follow the convention. If x is greater than or equal to 90, then the grade is A. Else, if x is greater than or equal to 80, grade is equal to B. So notice that else means x is less than 90. So this condition is false. And then at the same time, x is greater than or equal to 80. So in other words, if x is in between 80 and 90, the grade should be B, which is true, right? And then similarly, if x is between 70 and 80, the letter grade should be C. And if the score is between 60 and 70, the letter grade should be D. And the last statement is just an else statement. When the score is less than 60, then the grade is F. Okay, there is no if anymore. So the last else statement collects all of the cases that are not covered in the above conditions. So since x is equal to 85, which is in between 80 and 90, so the grade should be B. Lastly, let's take a look at a very special function, the if-else function. So this is a vectorized version of the if-else instruction. So the basic syntax is if-else condition A, B. If the condition is true, the whole function will yield A. Otherwise, it will yield B. For example, x is equal to negative 5. And if x is greater than or equal to 0, return x. Otherwise, return negative x. So in other words, the variable y is equal to the absolute value of x. Okay, since x is equal to negative 5, y is equal to 5. So this is a single value case. And this function is a vectorized version of if-else because it can handle vectors of conditions. So the condition can be a vector. So the condition can yield a vector of true or false values. In this case, the function returns a vector of the same length as condition with elements ai if condition I is true, otherwise bi. Okay, so let's see this example first. X is a series of consecutive integers from negative 5 to 5, so totally 11 numbers including 0. And if x is greater than 0, x, otherwise negative x. So notice that x is greater than 0 will yield a vector of true or false values, 11 of them. Right? And similarly, x is a vector of 11 values. Negative x is a vector of 11 values. So the function if-else will deal with the condition element-wise. For example, the first value is negative 5. And for negative 5, the condition is false. So the first element of y should be negative x1, which is 5. Okay? Second value is negative 4. The condition is still false. So negative and negative 4 will be 4. Okay? Consequently, the result will be like this. For all of those negative values, the opposite will be returned. Okay? And 0, okay, same thing. And positive values, the value itself will be returned. The point here is that the condition is a vector, and also the options are also vectors. If there are 2 or more conditions, then what should we do? We should use element-wise logical operators to combine those conditions together. For example, we generate 1,000 observations from the standard normal distribution using the R-norm function. And we know that for standard normal distributions, 99.7% of observations should be in between negative 3 and 3. So in other words, if a standard normal random value is greater than 3 or smaller than negative 3, that value is kind of abnormal. We will use this if-else function to identify those abnormal values. Okay, so the condition is x is greater than or equal to negative 3 and x is less than or equal to 3. So if you combine these two conditions together, it is x is less than or equal to 3 and greater than or equal to negative 3. So this is the normal range. Consequently, if a value is in this interval, then normal, right? Otherwise, abnormal. So the point is that both of these two conditions yield a vector of true or false values, and we can only use element-wise logical operators to combine these kind of vectors of logical values. Okay? And also notice that the results are single values, normal or abnormal. Is completely fine because if the dimensions are different, then we will recycle a and b in the function. So let's see the result of the simulation. Y is equal to this. So y is a character vector which contains either normal or abnormal. Okay. Let's use the table function to summarize the result, the distribution of y. Okay. It turns out that exactly 3 out of 1,000 values are abnormal and 997 are normal. So because this is a simulation, so it is really consistent with the theory of normal distribution. Similarly, if the condition is something like A or B in the if-else function, then we should use double bar instead of single bar, because double bar can handle vectors of logical values. Alright, that's all for this video. In the next video, we will talk about loops. For loops, while loops, and a special type of loop, repeat. And thanks for watching. See you next time. Hi, in this video, we will continue to talk about R programming. Today, we will talk about loops, for loops, while loops, and repeat loops. The most commonly used loop in R is for loops. Let's see one example. So we first define a sequence of consecutive even numbers between 0 and 10, using SEQ 0, 10, 2. So x has 6 even numbers between 0 and 10. Suppose we want to calculate the square of each number in x. We can do the following. First, measure the length of x using the length function and save it in n. So n is equal to 6. Then write a for loop. For parentheses, I in 1 colon n. 1 colon n is basically 1, 2, 3, 4, 5, 6. And then parentheses, y is equal to xi squared. Xi is the ith element in x. Last time we talked about how to extract a particular value from a vector using a square bracket, right? So this is the ith element of x, and we square it and assign it to y, and after that we print y. So in the first iteration, I is equal to 1. So y is equal to x1 squared, which is 0 squared. And consequently, when we print y is equal to 0 squared, which is 0. And then go to the next iteration, I will be equal to 2. Then y will be equal to x2 squared, which is 2 squared, which is 4. So that's why the second number is 4. Until the last iteration, I is equal to n, which is 6. x6 is 10. 10 squared is 100. So the last number is 100. And then the loop will be ended. So this is a for loop. So it works. However, it's not ideal because you see only the last number is saved in y. In each iteration, y will be overwritten. So the last number is saved, but the first 5 numbers won't be saved. Alternatively, we can first define an empty vector y. Okay, so see, we can use this. Y equals numeric n. So this will be an empty numeric vector with n elements. And then we will use this for loop to gradually fill the elements in y. So yi is equal to xi squared. And then all of the numbers will be saved in y. So this is a better practice. So let's see the general format of a for loop. For, parenthesis, index, in, nvec, parenthesis, action. So this index is called the looping variable. You can use any letter I, J, K, A, B, C, M, N. Any character string will work. And then in is a keyword. And nvec is a set of values that your index variable will loop over, will run over. Usually we will use a sequence of consecutive integers like 1 to 10, but it's not necessary. You can specify any set of values, may not be consecutive at all. And then we need to use curly brackets to wrap the statements in the action. So action is a grouped expression or group statement. And oftentimes the looping variable will be involved in the action part. For example, in the previous example, you see in each iteration, yi is equal to xi squared. So the looping variable I is used in the action part. So this is a for loop. And in R, loops can be avoided in many situations using a feature called vectorization. So this will make loops implicit in expression. For example, let's see, we have two vectors, x is equal to 1 to 10, and y is equal to -1 to -10. And n is the length of x, which is also equal to the length of y, because x and y have the same length. And then we want to calculate the sum of x and y. We first create an empty numeric vector z, then use the for loop to define each element of z. So zi is equal to xi plus yi. And then we print z out, we get a vector of zeros, because you see x and y are exactly opposites of each other. Alternatively, we can just add x and y together and assign it to z. We get exactly the same result. So this is called vectorization of the loop. So the loop is implicit. You see, still there will be 10 iterations, but we didn't use a for loop or any other loop. This vectorization of the loop is possible because in R, all calculations are done element-wise. We have seen many examples before. Okay. So because loops are slow in R, whenever it's possible, we try to use vectorization features of R to avoid explicit loops. But in practice, many times, the actions are quite complex, which involve very complicated calculations, so vectorization might not be feasible. Let's see the other two types of loops, while loops and repeat loops. So this is a standard syntax of a while loop: while, parenthesis, condition, action. A while loop will perform the action whenever the condition is true. The condition is a conditional expression which yields a true or false value. Whenever the condition is true, the action will be executed. Otherwise, the while loop will be ended. And repeat will repeat the action forever until it encounters a keyword break. So in general, repeat loops are more flexible than while loops, and while loops are more flexible than for loops. And it is a good practice to use the least flexible solution to a problem. So you should always use a for loop whenever it is possible. And notice that in order to use a for loop, you must know in advance the set of values you want to iterate over. However, in a while loop and a repeat loop, this is not required. You see, there is no index variable required in the condition part or in the action part of the repeat. Okay. Let's see some examples. First, a while loop. So this is a for loop we used before. Let's rewrite it using a while loop. So we first initialize a variable I, let it be 1, and then while I is less than or equal to n, we let yi be xi squared, and then we need to update the value of I. I is equal to I plus 1. We add 1 to I and then keep going. So at the end of the first iteration, I will become 1 plus 1, which is 2. And then go back and check. 2 is still less than or equal to 6. So the loop will continue. And then at the end of the sixth iteration, I will be equal to 6 plus 1, which is 7. And then go back and check the condition. 7 is greater than 6. So the loop will be ended. So if you want to use a while loop with an index variable, looping variable, you first need to initialize the value of the index variable. And within the while loop, you need to manually update the value of the index variable by adding 1 to it. Okay. So it's quite different from the for loop. In the for loop, because we have the preset value 1 to n, we know exactly the starting value of I and the end point of I. So we don't need to initialize I, and we don't need to manually update I. So if there is a looping variable that we can use, then a for loop will be a better choice than a while loop, apparently. Then I see a repeat loop. So let's rewrite the for loop using repeat. We first still need to initialize the looping variable I, let it be 1, and then repeat yi is equal to xi squared. Manually update the value of I. In the last iteration, I will be equal to 6 plus 1, which is equal to 7. Then we set an exit. If I is greater than 6, break. That means the repeat loop will encounter a break keyword, and the loop will be ended. So when we use the repeat loop, we need to pay attention. We have to set an exit so that the loop will be ended sometime. Otherwise, it will become a dead cycle and we will have trouble. Alright, that's all for this video. In the next video, we will talk about how to define functions by ourselves. Thanks for watching. See you next time. Hi, in this video, we will continue to talk about R programming. We'll talk about functions. Everything which is done in R is done by functions. And the function in the programming language is very much like its mathematical equivalent. It has some inputs called arguments and an output called the return value. And in R, a function can only return a single object. And of course, this object can contain multiple components. For example, the object can be a vector, a matrix, even a list. It doesn't matter, but as long as it is a single object, it's good. Let's first take a look at the structure of a function in R. Let's check the union function. This is a built-in function in base R. If we type union in the R console without parentheses and any arguments, then we can see the structure of it. So see, it's a function with two arguments called x and y. And in the function, it will first convert x and y to vectors using as.vector function, call them u and v, then use the c function to concatenate them to one vector, and finally use the unique function to find unique values in the combined vector. So this is exactly what a union operation will do. It will put two sets of items together and only keep the unique items in it. If we want to take a look at the arguments of a function, we can use the args function, args. For example, if we apply the args function on union, you will see the function has two arguments, x and y. And in particular, there are no default values for x and y. And x and y are the argument names. However, we don't have to specify argument names whenever we call a function, because each argument also has a position. If we put the arguments in their correct positions, then we don't need to specify their names. For example, A is a vector of numbers, B is also a vector of numbers. We can just say union A, comma B, then we get the correct result. So this is equivalent to the following line of code. Union x is equal to A, y is equal to B. So exactly the same. However, whenever you use the argument names, you can switch the positions of the arguments. You can say union y equals B, comma, x equals A. Many functions don't require all of the arguments to be specified. For example, if we want to generate 5 observations from the standard normal distribution, we can just say x equals r norm 5. 5 is the number of observations we want to generate. Okay. We get the correct result. We can do so because in the r norm function, the mean and standard deviation have default values. We can check it using the args function. We apply the args function on the r norm function. You see there are 3 arguments, n, mean, and standard deviation. And mean and standard deviation have default values 0 and 1 respectively. So that's why we don't have to specify them. If we omit them when we call the function, then mean will be 0, standard deviation will be 1. But n, the number of observations, does not have a default value. So we have to specify n whenever we call the function. And apparently the union function doesn't have default values for x and y. Let's see. Now let's see how to write functions by ourselves. It's quite simple in R. We just need to use the function. Okay. So first, give a name to your own function. For example, I want to create a function to calculate the square of an object. We can just call the function square equals function parentheses, then put all the arguments that are needed in the function in the parentheses. If you have multiple arguments, you need to separate them by commas. Then curly bracket, write down something you need to do in the function. In my simple function, I just need to return the square of x, so just put x squared here. After I define the function, I can immediately call the function. Square root of 5, which is 25, correct. Just pay attention for self-defined functions. Whenever you want to use it, you need to define it. That's because after you quit R, the function you defined will not be saved usually, unless you save the workspace, which is not recommended. Whenever you reopen R, the function you have designed does not exist, so you have to redefine it. So that's why it's important to save your code in a script or some other file so that you can reuse it later. Pay attention that objects or variables which are created inside a function do not exist outside of it. Take a look at this example. I created a function to calculate the mean of a vector. I call it mean2 because in R there is a built-in function called mean. So mean is a reserved word in R. To avoid confusion, I use mean2. So the function will first calculate the length of the vector x and then divide the sum of x by the length of it, which is exactly the mean of it. Okay, so the function works. It seems that m is defined in the function, but m does not exist outside of the function. If you type m in the R console, you will get the following error message: object m not found. That's because m is an intermediate result in the function and is not recognized outside of the function. Just pay attention to that. Now let's see some examples of writing functions. We have learned conditional flows. Actually, conditional flows are important building blocks of self-defined functions. For example, if we want to create a function to calculate the absolute value of an object, we can do so, call it ABS2, again because ABS is a built-in function in R, so that's why I name it ABS2. And it's a function with only one argument, x. If x is smaller than 0, the output is equal to negative x. Otherwise, out is equal to x. And finally, I will return out. And then the function is done. Then test it. Put negative 5 in the function, we get 5. Now let's see an example of writing a function using loops. Suppose we want to define a function so that we can calculate the factorial of a positive integer. The factorial of a positive integer is the cumulative product from 1 to the integer. For example, 3 factorial is equal to 1 times 2 times 3, which is 6. And 2 factorial will be 1 times 2, which is 2, etc. So let's write a function to calculate it. I call it factorial 2. Again, factorial itself is a built-in function in R. So pay attention, now we assume that the input n is a positive integer. So first out is equal to 1. Then write a for loop. For I in 1 to n, calculate out equals out times I. So let's see how it works. In the first iteration, I is equal to 1. So out is equal to out, which is 1, times 1. So after the first iteration, out is still equal to 1. And in the second iteration, I is equal to 2. Then out is equal to 1 times 2, which is 2. And then in the next iteration, out will be equal to 2 times 3, which is 6. Okay, so the for loop helps us to calculate the cumulative product. And eventually after the last iteration, out will be equal to 1 times 2 times all the way to n, which is exactly what we need. Let's test it. Factorial 25 is equal to 120, which is correct. Okay, you can verify it using a calculator. In the previous example, we assume the input is a valid input, which means n is a positive integer. What if n is not a positive integer? In this case, we need to use an if-else conditional flow to filter out invalid inputs. And if the input is invalid, we should provide an error message to remind the user that your input is not correct. So we can do the following. If class is equal to numeric, so it's a number, and round n is equal to n. So this guarantees that is an integer, and n is positive. If all of these three conditions are true, then we calculate the cumulative product and return out. Otherwise, print an error message. The input should be a positive integer. Let's test it. When n is 5, we get a regular result. When n is not an integer but positive, we get the error message. When n is negative, we also get an error message. Great. How about n is equal to 0 case? We know that 0 factorial by definition is equal to 1. And our previous function cannot handle n is equal to 0 case, actually. It only accepts positive integers. So to accept 0, we need another layer of if-else. We can do the following. If n is equal to 0, out is equal to 1, I return out. Because by definition, 0 factorial is equal to 1. And else if we check the three conditions, so this will handle the positive integer case. We'll calculate the cumulative product. And if any of these three conditions is false, then print the error message. Let's check the result. When n is equal to 0, we get 1. When n is equal to 3, we get 3 factorial, which is 6. When n is negative, we get the error message. And if n is actually a character string, then we also get an error message. Alright, that's all for this video. In the next video, we'll talk about the apply family of functions. They are very efficient functions that we can use to do data management, data summary, etc. Thanks for watching. See you next time. Hi, in this video, we will continue to talk about R programming, the apply family of functions. Coding often involves repeated application of the same function to different pieces of data. The apply family of functions are used to perform these kind of tasks. They are essentially implicit loops. Functions in the family include apply, lapply, sapply, replicate, and tapply. First, the apply function. This function is used for matrices. The basic syntax is apply x, d, and f, where x is the matrix or the data frame, and d is the dimension of x. D equals 1 is corresponding to the rows. D equals 2 is corresponding to the columns. So when d is equal to 1, then the function will be applied on rows of the matrix. When d is equal to 2, the function will be applied on columns of the matrix. And f is the function that will be applied. So basically, the apply function means applying function f to each of the d's dimension of x. For example, we first define a matrix A, which is a 3 by 3 matrix with integers. Then suppose we want to calculate the mean of each row. Then we can do this. Apply A1D. D is equal to 1, so we will calculate the mean for each row. The first row has 1, 4, and 7, so the mean is 4. And the second row has 2, 5, and 8, so the mean is 5. Similarly, if we want to calculate column means, we can let D be 2. Then we will calculate the mean for each column. So 2, 5, and 8. The second function is the lapply function. If we want to apply a function to every component in the list or a vector, we can use this lapply function. L stands for list. The syntax is lapply xf. Only 2 arguments. X is the vector or list, and f is the function. Because lists and vectors are one-dimensional, it's not necessary to specify the dimension anymore, so we don't need the argument d anymore. And the lapply function returns a list of the same length as x. So if x has n elements, the result of lapply will also have n elements. Let's see an example. N is a vector with 3 integers, 5, 10, and 20. Then we will apply the rnorm function on n using the lapply function. The rnorm function is used to generate random numbers from normal distributions. If we omit the mean and standard deviation arguments, then we will generate numbers from standard normal. And there is one necessary argument, which is the number of observations we want to generate. So in this case, this vector n provides the values for that argument. The function works in this way. First, rnorm is applied on 5. So rnorm 5 will generate 5 numbers from standard normal. And then rnorm 10. So we generate 10 numbers from standard normal, etc. And we save the result in out. Out is a list of 3 components because n has 3 numbers. So take a look at the result. So out is indeed a list of 3 components. We can further apply the mean function on out. Out is this list, right? Suppose we want to calculate the mean for each sublist. We can call the lapply function again. And the function we apply on out is mean. So we'll calculate the mean for each sublist. So this is the result. And again, the final answer is still a list because we use the lapply function. If we don't want it to be a list, we can use the nlist command to turn the result into a vector. And there is a function, the sapply function can do it automatically, which means it will take a list and do the calculation and finally return a vector. For example, if we use the sapply function instead of the lapply function, we get a vector of means. The next function is the replicate function. Sometimes we wish to repeat exactly the same operation many times without changing anything. In this case, we can use the replicate function. There are only 2 arguments, n and f, where n is the number of times we want to repeat the application, and f is the function. For example, we want to generate 3 samples. Each contains 10 standard normal numbers. We can do the following. Replicate 3 rnorm 10. Okay, so do this 3 times and save the result in out. Okay. So by default, the result will be saved as an array. So it's a 2-dimensional array. Each column is a vector or a sample. So totally 3 samples. If we want the result to be a list, we can add an argument, simplify equals f. Then the vectors will be saved as a list. So each vector is a sublist of a list. So out will be a list if we specify simplify equals false. And lastly, sometimes we may wish to evaluate a function on data in a vector or list, which are grouped according to the levels of some other factor. So namely, sometimes we want to summarize some numerical variable that is grouped by some categorical variable. In that case, we should use the tapply function. Let's see an R package called Titanic. This one contains data sets providing information on the passengers on Titanic. And the variables include economic status, sex, age, etc. So in order to use this package, you have to install it first and then load the package. I also load another package called dplyr because I want to use the glimpse function in the package. And by the way, the data set is split to two parts, a training set and a test set. The data is split for the machine learning modeling purpose. We will only use the training set. So call the glimpse function. Take a look at the training set. You see there are 891 rows and 12 columns, 12 variables. And survived, this one is a response variable which represents the survival status. 0 means died, 1 means survived. Okay. And passenger class, name, etc. Okay. Suppose we are curious about the survival rate between the two sex groups. We can use the tapply function. Notice that I first attached the data set. That is because for any data set, the variables are not directly available to us. To use a variable in a data set, you have to refer to the data frame. So if we don't attach the data set, you have to always use the data frame. For example, Titanic _ train $ survived and Titanic train $ sex. So you see, the code will be very tedious and long. To avoid that, we attach the data set, and then all of the columns, the variables, will be available to us. Alright, now let's focus on the tapply function. So the first argument is the vector of values that we want to apply the function on. It should be a numerical variable. And the second argument is a grouping variable. Usually it's a categorical variable or a discrete numerical variable. In our example, it's sex, okay, sex group. And the last argument is the function we want to apply on the numerical vector. So the mean is the function we want to apply on survived. Because survived is coded as 0 and 1, so the mean of this column is equal to the proportion of people who survive. Alright, so this is the result. So the female group has a survival rate about 74.2%, and the male group has a much lower survival rate, 18.9%. It's also possible to use 2 or more variables to group the data. For example, we might be interested in comparing the survival rate among different passenger classes and sex groups. So we can use both of them to group data. Just don't forget to wrap them in a list first. And then we get this table. So we can read the numbers horizontally within the female group. As the class increases from 1 to 3, the survival rate decreases. We see a similar pattern in the male group. Okay? As the class increases from 1 to 3, survival rate decreases from 37% to 14%. And vertically, the survival rate of the female group is always greater than that of the male group for each class. And after we use the data set, we should detach the data set. Alright, that's all for this video, and also this is the last video of the introduction to R programming series. Thanks for watching. See you next time.